In this video, we will simulate flow through a manifold microchannel heatsink using Quanscient Allsolve. For this demo, I chose a very recent paper from the International Journal of Heat and Mass Transfer. In this paper, the authors simulate the flow in the manifold microchannel heatsink. Their goal is to optimize the thermal performance of the heatsink by modifying the geometry of the microchannel. Here you can see a schematic of the manifold microchannel heatsink. It contains the horizontal slots which form the microchannels. The solid bars above form the manifold geometry. The blue arrow indicates the cold fluid coming in the microchannel, which heats up, taking away the heat from the sink and leaves as indicated by the red arrow. In the paper, authors choose a small section of the geometry as shown in the right picture. Uh, The microchannel geometry is defined by various dimensions. The heatsink itself is made of copper, and the fluid flowing in the channel is deionized water. In the paper, authors simulate various geometries and characterize the flow, thermal performance, the pumping power, and the pressure drop across the channel. In this video, we will fix the geometry to a straight channel which corresponds to alpha equal to 1. And run various simulations with various volume flow rates using Quanscient.Allsolve. We will try to reproduce the rate curve shown in these plots. Okay, let's start. We create a new project. Let's name it manifold microchannel heatsink. We start with create a geometry. We can start with any shape. I will start with a box because I know that I will need many of them. So we get a default box of 1 by 1 by meter, 1 by 1 by 1 meters, and yeah, we can start editing. I will need few of them, so I will try to quickly create these boxes. Apply and build. So as I input micrometer scale values, we have to first reset view to see that box, and you can see that the box is created. I need few more of them so I can create another box. I need to position this box at certain locations, so I will start inputting values. And the different sizes. Build. So this is the second box. I need another box which I have to position at this Z location with XYZ dimensions. Yeah, so I have created box. I need one final box. Yeah, so now I have all the boxes which I need, and with these boxes I can start creating the required geometry. First I need to fragment all the boxes. So this will create a different number of volumes, and now I can make a union or remove the volume. So first I will union some of the volumes. So what I want to unite is the water region. Yeah, so this is our water region in the channel. Then I want to remove these middle volumes, so I can remove them using remove operation and build. So now you can see we have two volumes left, one which is copper and the other is the water. Confirm model changes and the model will be locked. The geometry, we can start assigning the properties. So click on the properties tab. We first assign materials. So we need copper and we can assign this volume to copper region, and we need water, and I assign the properties of water to this region. So the volume regions are already created as we assign the properties to these volumes, but we will need a few boundary surfaces to apply boundary conditions later. So let's start. So we need inlet, then outlet, then some slip wall in X directions. So we will force the water or stop the water flowing out of these boundaries, but the fluid or water can move along these boundaries. Another slip wall in Y direction, and we need a adiabatic water. So this is basically the surface is touching the manifold bar. So the we apply the insulating boundary condition to these boundaries, so no heat can flow across these boundaries. Then we'll need to apply the wall boundary conditions. So no slip wall boundary condition to the interface between wall and copper, water and copper. No slip wall. I need to deactivate first the volume and then select the surfaces. So I can select this, this and these surfaces. And these will be the no slip walls, and these will act as the interface between the copper and water, and there will be heat transfer across. And we need one more surface. Let's name this CHT walls. We need another surface where we apply uniform heat flux. This is the bottom of the sink where the heat is coming from. Yeah, that's it. Let's move to the physics section. So let's add heat transfer. So heat transfer will be applied to copper and apply the laminar flow to water region. We have to create some interactions. For example, in the heat transfer, we have to define the heat source at the bottom of the sink. So let's select uniform heat flux. We know the value from the paper. Then that's it for the solid region. We have to create several boundary conditions. So velocity inlet for the water region. So let's visualize the volume, water volume again, and yeah. So let's select inlet, as you can see here. So we know the velocity is in z direction, and specifically in negative z direction. We know the volume flow rate, which is 0.01 milliliters per second. We have to convert it to cubic meter per second and divide it by the inlet area, which is 0.3 by 0.3 square meter. So that's our inlet velocity. Then we have to define the pressure outlet. Let's select the outlet boundary and we set the value 0. Then another velocity constraint for slip wall in x direction. So we force the flow along the other two direction, but we don't allow the flow through to move across the boundaries. So we stop the flow movement in x direction. And for other two directions, we can set the component wise velocities. This will simply set the velocity from the fluid region. So it's equivalent to setting the Neumann boundary condition. We can also deactivate the other two components, and this will be also equivalent to Neumann boundary condition. Then another slip wall in y direction. So we have to set the y component to 0 and other two components as Neumann boundary condition. Then the adiabatic walls. These are no slip walls. So we have to set all three components to 0. Then CHT walls are also no slip boundary condition, and that's all. Now that we have defined all the boundary conditions and interactions, we can move on to simulations tab and add new simulation. And yeah, before we can start running anything, we have to create a mesh first. In this case, I will use expert settings because I know how the mesh should look like. And yeah, I will start the meshing. In this case, we will enable scripting because you might have noticed that I added two different kinds of physics, so namely laminar flow and heat transfer, but I haven't added a coupling between them. So there is no interaction, there was no interaction defined between the laminar flow and heat transfer, and this we will do using scripting. So once we click on enable scripting, the scripts are created automatically and all the settings are available in this script, and you can edit any any setting that you have previously created using the different tabs. So in this case, as you can see, we have the heat transfer defined for the copper region. Then there is a uniform heat flux applied, uh, and there is laminar flow. So, but we haven't defined any physics or any uh, governing equation for the temperature field in the water region. So that's what we have to add. And we will add this. So we have to add conduction and uh, convection in the water region. So heat conduction and convection in water. So we to the existing formulation we add another integral. This time choose the water region, and we have predefined advection diffusion equation. So in this case we can define this advection diffusion equation for the temperature field. It takes several arguments. First, the degrees of freedom. So this is the unknown temperature field. Then we need the test function. Then velocity field, material properties of water. So thermal conductivity. This is the flag for setting the transient or the unsteady term, which in this case we have steady state simulation, so we set it to 0. Then again material properties of water, density times the heat capacity. And the last flag is for the divergence. So if the for incompressible flow the divergence is 0, so we have to set it to true. So we have added the predefined advection diffusion equation for the temperature field for the water region. So that is not enough. We have to also add the initial and boundary conditions for the temperature in for the water region, and that's what we have to add before. So I will set temperature. I see initial conditions and boundary conditions for fluid region. So we create some reference temperature, 293 Kelvin for example, and create the initial value. So here we can select all regions, so including the solid copper region, and here we set initial velocity, initial temperature to reference temperature, and yeah, then the boundary condition for the water region. So using set constraint for the water region, and I want to set this inlet temperature condition to 293 Kelvin. And before we move on to running the simulation, we have to also add some post-processing step. So this could be added using the outputs. So we can add all the fields. So this will be 3D fields. These will be 3D field output. We can also manually add this in the script after the solve, and this will be the set output field. So we can create as many uh, output fields as we want. And apart from the 3D output, we also need to have the uh, we need to calculate some integral quantities, for example, thermal resistance or even the pressure drop across inlet and outlet, and this has to be defined here as well as a post-processing step. So let's start defining post-processing. Another integral quantity to have a check on your simulation is just checking the inlet and outlet flow rates, and we can define this as flow rate in, and I'm creating a normal to the region, water region, and taking the dot product with velocity, and this I have to integrate over the inlet region. So this will give me the flow rate integrated over the inlet. Similarly, we can create flow rate at the outlet. I'll just copy this, and the normal now has to be the other way. The signs don't matter. I mean, you will know the value anyways, and the signs just indicate the whether the flow is coming in or out, and these normals are usually pointed outwards the region, and if the velocity is also going, if the fluid is moving out and it's moving along the normal direction, so you will get a positive value. And for the inlet, this is the opposite, so fluid is moving in the region and the normal is in the opposite direction. So if we take the product of this, you will get a negative value, and to avoid that, I have a negative sign here. Then we have to create pressure drop across the inlet and outlet. Let's first define the inlet pressure. So we have field P, and we want to create the surface averaged pressure at the inlet. So first we integrate the pressure at the inlet region, and divide it by the area of the inlet, so area average pressure. So it's simply I'm integrating value 1 over the surface, which gives me area. Similarly, the outlet pressure, I'll just copy for the outlet region. So this will give me area averaged pressures at inlet and outlet, and we can compute pressure drop simply taking the difference. So I'm taking absolute difference to have a positive value. To calculate the thermal resistance, we have to compute several quantities as defined in the pressure. So first, let's calculate the base temperature. So it's maximum base temperature, T base max. We have to start with the temperature field. Can take all max. By the way, all max is just simply taking maximum over all regions. And similarly, all integrate was also doing integration across uh, all regions or all um, if you are running the simulation in parallel, so you split the uh, domain into several pieces, and this integrate does integration across all pieces. If your inlet is divided into different uh, divided on different CPUs, then this will take care of that. Similarly, all max is taking max over all domains. And we have to compute this on uniform heat flux boundary. Then we have to also compute minimum base temperature. So we have all min for that and the average temperature. Here again we have to use all integrate over region uniform heat flux divided by the area so yeah, this will give us the surface averaged base temperature, and as defined in the paper we have to set the area of the heat sink, and this is the whole area, not just the base area. So it has been given in the paper. The dimensions of this whole heat sink are 10 by 11 millimeters. So I simply compute this in meters. So this is area of whole heat sink, not just the small section that we have chosen for simulation. And then the thermal resistance. Thermal resistance is calculated as T base max minus T reference by expression by Q, which is the heat flux. So in this case, we have set the value for the heat uniform heat flux and the area of the base. Yes, so this is all. Then there are other parameters that are defined in the paper, for example, pumping power, then mean absolute temperature difference, and these can be also calculated. And once we have calculated, we have to also write them in some file, and I will not go through these line by line, but yeah, it's simply writing a CSV file for all these calculated values. So for example, flow rate, inlet outlet, we haven't defined average wall temperature here. Let's just define it before, and yeah, then these are conveniently scaled to have milliliters per second. Pressure drop is in kilopascals, and yeah, so this output will be written to the statistics.csv file. So before we start the simulation, let's take a look at the script again, just to make sure that everything is correct. Yeah, this has to be inlet boundary condition, not the full water region. Um, Other things look fine. Redefine advection diffusion, all solve, set output field, um, yeah, all the post-processing parameters and all. Yeah, the script looks good now. Let's take a look at mesh. Looks good. Now let's move on to setting up simulation. Let's name it demo, node count 1, and we choose one CPU with 16 gigabytes of RAM. Set the duration of simulation to 60 minutes and run simulation. You can take a look at logs, set auto scroll true. The simulation is starting. Here we can see the relative change in successive iterations. It's a nonlinear solver. It converges within 5 steps. And once it is converged, we can take a look at 3D fields. So let's activate the visualization, then add the velocity field. Yeah, we can see the velocity field and the values. We can also create some glyphs. We can scale it so that they are not big arrows, and we have to click render. Yeah, so there's nice flow going from inlet to outlet, and we can also add the temperature field. We create a slice into that, and yeah, we want to look at the temperature field through the fluid region as well. So I will move the plane towards negative x direction so that it intersects with the fluid region, and apply and render. Yeah, so you can already see some temperature field. I want to change the color scale for the temperature field. Let's select this one, and yeah, so you can already see that the flow is taking away some of the heat. See the temperature gradients and looks reasonable. Uh, yeah, apart from 3D output, we also wrote a file, and yeah, we can take a look at that file. So we have to first go to the demo tab and download. We can download other results which contain. You can also download VTU files, so all the 3D output files and the CSV file will be written into the other results. The zip file is downloaded into a local machine. We can unzip the file. We can take a look at statistics.csv that was written, and you can already see the parameters. So the flow rate is quite close to what we set. Both at inlet and outlet, we have the average wall temperature at the interface of water and copper region, then the pressure drop, 0.16 kilopascals, thermal resistance, pumping power, and also the mean absolute temperature deviation. So we got the values for one data point. As we said in the beginning that we want to reproduce the plot for different several volume flow rates. So for this we can use the sweeps feature. So for creating sweeps we have to first create the expression, shared expressions. So let's first create volume flow rate because we want to simulate the same case for different volume flow rates. Volume flow rate in, we have to use milliliters per second, and here we set one value and we will edit this value later in the sweeps tab. So this is the default value. Once we have set the shared expression, we go to the simulations tab, click on the sweeps and create a sweep for volume flow rate, and you can easily create starting. So this the starting flow rate, the final flow rate, and how many steps you need in between. So we have to do 10 steps. We have to still edit the volume flow rate in the script. So we had set here the uh, volume flow rate, and we have to add the shared expression instead of the value. And now this will automatically take the values for different simulations. Once this is set, we can hit the restart tab, and all 10 jobs will be submitted simultaneously. So all 10 simulations are now running simultaneously on the AWS server. Some of the jobs are finished already. All sweep jobs have now successfully finished, and we can go to download tab and download the other results which contain the CSV files. After downloading the CSV files, I created the plots of thermal resistance versus volume flow rate. Here the symbols indicate values from the paper, and the solid line indicates the results from Quanscient.Allsolve. As we can see, there is a relatively good match between the two, although there are differences at higher flow rates. If we take a look at pressure drop, we can see that there are differences between our simulations and the values from the paper. But those could be simply due to the coarse mesh that we have used in our simulations. In this demo, we saw how to set up a manifold microchannel heatsink simulation in Quanscient.Allsolve. We also saw how to set up the parameter sweeps to perform multiple simulations simultaneously, which could be very useful in optimization studies.